Okay, it's my great pleasure to introduce Yordan Zaykov, who is our first speaker for this session. Yordan is Research Engineering Manager at Microsoft Research in Cambridge, where he leads a team of talented machine learning scientists and developers. His research interests revolve around probabilistic modeling and knowledge discovery. And his passion is taking research projects and applying them to real-world applications. Examples of the latter include Microsoft's machine learning-based cloud platform, Azure ML. He's also worked on the predecessor of the focused inbox clutter, the TrueSkill rating system for online player matchmaking, and what Yordan's focus lately has been is Viva topics, which automatically organizes enterprise knowledge into shared topics. So let's thank our speaker and welcome him onto the stage. Thank you.
Thanks so much. Cheers. Thank you. Can you guys hear me well? Yeah. Great. All right. Yeah, so my name is Yordan. I work at Microsoft Research here in Cambridge in the UK, and I'm very happy to be again here at AKBC because I am literally going to talk about automated knowledge-based construction today. So for the better part of the last decade, I've been working on Project Alexandria, which is a research project in Microsoft Research. And a couple of years ago, research from this project shipped in a new Microsoft product, which is called Viva Topics. So what I thought would be most useful to do today is to walk you through some of that journey and to actually look at some of the learnings along the way. Now, the way I'll structure this is that we'll look at the product, we'll look at what requirements the product has, and how this translates to requirements on the machine learning and the technology that actually has to construct the knowledge base. Okay, the hope is that people will be better aware of these requirements so that when you build components that are part of the pipeline in automated knowledge-based construction, you can do this in a way that this is pluggable with the rest. All right, let's dive in. So first of all, Project Alexandria is all about automated knowledge-based construction, but it has a machine learning component and also has an HCI component. So the latter is about figuring out how to surface the knowledge into user experiences. So as I said, this shipped into Viva, which is a Microsoft product, so try to distinguish the two, so that the research project and the actual product, they are different. But Alexandria powers Viva, which is all about employee experiences, and it has different components, different pillars, if you will, one of which is Viva Topics, and this is the part that focuses on knowledge. So if you look at Viva Topics, I stole this slide from our product team. It's described in a very similar way as the mission of Alexandria, which I really like. So it has to do with organizing the content in the enterprise into shared topics. So this is the automated knowledge-based construction part. But then also it has to surface these topics into user experiences. And this example here is given to share the knowledge in a kind of a wiki-like. So you can think of it as automatically constructing a wiki for the enterprise and then using it in various experiences. So what I'll do is that I'll give a quick demo of Viva Topics, because then we'll try and work out what are the requirements of the product and then how this translates into machine learning requirements. All right, let's go. So let's say that you are somewhere in your intranet, which is powered by Microsoft 365, which is our suite of productivity tools. In this case, you're in, I guess, in Viva Connections, but you can also be just in a SharePoint site. And what you might notice here is where we say the breaking, we are proud to announce the release of Mark 8. Now we've automatically highlighted this Mark 8 because we've recognized that this is an entity that we have previously mined from the enterprise data. So what the user can do is that they can go and click on this highlighted value, and what shows up is what we call a topic card, which really is this kind of concise view of the topic. Topic, you can think of the topic as knowledge-based entity. It seems to be the term that users relate to better. Right, so you can go at the top of this topic card to view details, and then you get the topic page. The first thing that you notice on this topic page is that this screenshot was taken in a screen with a much lower resolution than here. I apologize for that. But then you see that the topics have a schema and they have all of these different properties. So they'll have a primary name, they'll have a list of alternate names, they'll have a description, and they'll have all of the experts on this topic, various resources like like documents and pages, and they'll also have related topics. And we keep on adding more and more properties to the schema that the machine learning supports. For instance, we recently added a type, so you know if something is an event or a service or a project and so on. And that was automatically built, which is pretty cool, I think. Right, so it's surfaced in various experiences. As I say here, you can see it in Teams. You see this SOAR was highlighted in a message. You can again click on it, and you can see what the topic is. Now, if we haven't highlighted something, you can actually select it in one of our apps. In this case, you see this Mark 8 here. You can select it, and you can search for Mark 8. And then the search will actually, hopefully, return the entity if we have mined it, but we didn't highlight it in this context. You can actually also force highlight something, like you can hashtag it. For instance, in Teams, if you write a chat message, you can do a hashtag and start typing a name, and this will let you select from the list of topics. Right. So then you can also manage these topics. This happens in a place that we call Knowledge Center. In this case, it's integrated as in this example, is integrated as an app in Teams. And you can go and you can browse your topics. You can go to the published topics, for instance. You can look at the topics, and let's say that you can click on one of them called Project Blue. And I selected this one because I have a higher resolution screenshot. So what you can do here is you can go to the top right if you see that there is Edit. So you can click on Edit, and you can actually edit the topic. The topic attributes. You can, for instance, in the description, you can write a better description. You can write different alternate names or anything else of the schema, but you can also add new properties as well. Right, so that's pretty much it. I hope I managed to fit that in less than 5 minutes. It has to do with automatically organizing the content into these topics and then surfacing them in various user experiences. Is that more or less clear? Yeah, all right, cool. Now what we're going to go over is the requirements of the product, and then we'll see how this drives the machine learning algorithms and models that we develop. Right, so starting firstly from the inputs, these have to be the data as it is in the enterprise. So you're not going to ask the users to change the data for you to mine more easily from it. You have to work from what you've got. Then you actually have to build topic pages. As opposed to just answering questions or providing a list of snippets. You really need to build these things. So it is about knowledge-based construction. And then on the output, you have to figure out how and where to surface all of this knowledge that you discovered. And while doing all of this, you have to preserve privacy, because that's super important. And you have to support the KB, which evolves over time. So it's not a batch process that you do it once and you're done with it. It keeps going. Now there are very many requirements that I can keep going, like dealing with data that is geographically distributed in international companies, scaling to billions of documents, supporting multiple languages and generalizing across the various customers that we have. And there's actually many, many more. Now, I can't list all of them, so I'll just focus on the part that I think is worth sharing here. So I'll actually talk about the first 5, okay? And we'll see what machine learning requirements these drive. Now, the first one was about working from the available enterprise data. Now, this data is actually very diverse. So you have all of the unstructured sources, which are themselves very diverse. So you've got emails, documents, chats, and so on. You have to be able to mine from that. Then you have all of the structured sources. Examples here include external knowledge bases or ones that the enterprise have already built themselves. You have to be able to include these in the enterprise knowledge base that we build. You also have to support mining from the metadata, things like the recipient of an email or the author of a document. That information also needs to be included because it's extremely valuable. And finally, because this set of inputs is so diverse, you can't assume that all of the property values will be available to you when you start linking things together. So there will be missing values there. In one case, you'll have maybe an event which has a name, date, and an organizer. In another place, you'll have name, date, and a location, and you have to be able to merge these two. So you can't assume that all values are always available. Right, okay, one down, 4 more to go. The next one is about actually building the topic page. I don't know how to write this, but it really is, you have to be able to create that concise, structured view of the topic that you need to present to the user, right? So it's not an answer to a question, it's not a list of snippets of search results, you actually have to build it, right? So what this means is that you have to be able to take the information that's available and somehow merge it into one place that you would display to the users, right? And as you do this, the users would actually expect the topic information to be complete, but as you merge information, you shouldn't over-merge, or what I'm referring to is making mistakes in the linking. For instance, if someone has project ACE and in another place the acronym ACE, and they refer to different things, you shouldn't be merging the property values together, which I refer to as over-merging here. All right, moving on, surfacing the topics in various user experiences. Probably one of the most important ones is the human curation. So users want to edit, they want to add, they want to remove topics. So you have to support the human in the loop, and that happens continuously, right? So also for things like highlights, when you build the knowledge base shouldn't be fragmented because you wouldn't know which one of the fragments to select. And even if you select one of the correct fragments, it will be incomplete because the remainder of the fragments will be all there. So what you want to do is, as mentioned on the previous slide, not over-merge, but also not under-merge. So your linking has to be really good. And finally, it's worth pointing out that the knowledge graph that we construct has to be materialized, is the term, because users have to be able to browse it. They have to be able to discover topics. So it has to be actually all there. Okay. Now, in terms of privacy, privacy is a research problem. I guess it's both research and engineering problem, but it is not something that you can just tell people to engineer. You can't give them, here's a large language model, use it as a knowledge base, but you engineer how it tracks provenance, right? So we have to think about it as we develop the algorithms. And there's at least 2 things that come to mind here. The first one is that a lot of the data, most of the data, is actually eyes off. You cannot see it. Okay, it's customer data. We don't have access to it. Maybe in your tenant, if you're an employee of the company and you develop the algorithm, I guess as it is my case, I will be able to look at the data that I have access to, but in general, most of the data is eyes off. So you truly have to do automated knowledge-based construction. You can't be there, look at the data and guide the algorithm. It has to be automated. And then secondly, as you build the knowledge base, you have to track provenance because permissions are actually always checked at real time. Even if someone had access to something when the knowledge base was constructed, then when you surface the topics to users, then this needs to be checked again whether they have access to this information because they might no longer do. So you really need to track provenance. Right, and finally, the KB actually evolves over time. So it's not a batch process, right? So what this means is that as new information arrives, you can't just recompute the entire KB because then it will not be stable. People will not see what they expected to see because it was previously there. Things like hashtags have to continue working, right? If they were previously pointing to a given topic, they have to continue pointing to the same topic. The same is true with links to topic pages. So you have to be able to provide stable identifiers to entities over time. And finally, the KB has to be fairly fresh. It has to be up to date. So this also means that you can't really use a batch process because it's very slow. So you have to support incremental learning in your machine learning model as it evolves over time. All right, here's a quick summary of all of these requirements. Now this is probably one of the most important slides in the deck. So I'll just go over them. You have to support structured and unstructured inputs. You have to prevent both over and under merging. You have to support missing values in linking. You have to support merging of fragments and the human in the loop. You have to support incremental learning, tracking provenance. You have to maintain stable entity identifiers over time, and you truly have to construct the knowledge base automatically. Right, so note that this is the ones that I've derived from the selected ones, so there's actually many, many more that I'm not just going into here. But things like multilingual, multi-geo, and so on, there's many, many more. And I selected these because I think many of them actually refer to a component of the pipeline in automated knowledge-based construction that I don't read so much about. This is the part about linking and merging. I think there is actually a lot about linking, but not so much about merging, right? So when you take the entities, which might be fragments at that point, fragments of entities, and you put them together when you construct the knowledge base. So that part has to satisfy all of these requirements. Right, so what I'll do is to try and provide a framework in which we can solve this. Are there any questions at that point? No, everyone is happy. Great, all right. That's fantastic. Cool, right. So let's see. I'll also build this up as I do. So I'll start from the way we see the knowledge base, and it's kind of an object-oriented view of the knowledge base, which I don't know that if everyone can relate to, but I try to depict it here in pseudocode. So we have an example of an entity type, which in this case is an event, and then there is an instance of this type, which is the actual entity. This is AKBC in this example. And the corresponding type has a given schema, which is the set of properties, and in the instance you have the actual property values. Now what's very important is that all of these properties have corresponding types, and these are, in our case, probabilistic types. Okay, that might be unclear. So what I thought I would do this time around and talk a little bit about the probabilistic types. So the probabilistic types have to do these 5 things. Okay, so they have to know how to read themselves, so they know how to look at the text and then convert this into a distribution over strongly typed values. So you can think of like reading an uncertain property value. Right, so if someone wrote this product will launch in November 2022, then if you read this date, you would have a date which has a point mass in November and point mass in 2022, but probably has a uniform distribution over the days of the month. Okay, so that would be an example of an uncertain property value that you would read. Then it has to know how to write itself, because we'll have to display these things. It has to define a prior distribution over the range of values it supports, and it has to be able to provide an actual, like this distribution. When it reads itself into a distribution, it has to support these 2 operations in this distribution, which are inner product and product. Okay. So I'll give a quick example here. This will be a toy example because real examples don't exactly fit on one slide, but this will translate to very many property types, probabilistic property types. Okay, so here we have 2 textual representations of uncertain dates, I guess. So the first one is the event took place after Monday, and the second one is the event took place before Thursday. So if we try to read these and convert them into distributions, what we would have is that in A we'll have a 0 for Monday and 1/6 for each one of the other days of the week. And in B we will have 1/3 for Monday, Tuesday, and Wednesday, and zeros in the remainder. Okay, that should be clear. Then if you define a prior, priors are, the model isn't too sensitive under the priors, but they can be very useful. I'll give some examples. You can usually go with the uniforms though. So in this case, we can go with a uniform prior. However, if you are defining something like a type of an actual date, then the prior there, you might choose it to be uniform over the days and over the months, but in the modern internet era, you probably don't want it to be uniform over the years. I think actually years from ancient times are less likely to be present in dates that you encounter. So you can refine your prior, but uniform is fine here. Right, so then you have to be able to define the inner product and the element-wise product. This is easy in this case. The inner product is just the product of the corresponding elements added up. And you can think of it as the, if you draw two values from the two distributions, then what is the probability that they're the same, right? So what's the probability that you sampled the same value? And that's the very useful information that you will incorporate in the linking algorithm, okay? Now the element-wise product is, in this case, will just be Tuesday and Wednesday, right? Which after normalization, you get this distribution here. By the way, when you compute the element-wise product, the normalizer is the inner product. So in reality, we don't compute them separately. In a lot of our models, the inner product is a part of the computation of the product. However, I decided to write them this way here because if you were defining a model over embeddings, then you might want to approximate them differently, right? So what you would do there is that, because we've already done that, by the way, you can have a uniform prior on the embedding, and then if that's let's say it's a large language model embedding that was trained on cosine similarity, then you can build a model that takes the cosine similarity and actually spits out the probability that these two embeddings refer to the same entity, right? So you can actually implement the API of this probabilistic type over embeddings. And if you look at in my previous slide, where did I have description? These descriptions are actually the type, which is we have a generic text type. You can implement it through a bag of words, but you can also implement it through an embedding if you want. So it's very nice that it allows you to compose, I guess, the probabilistic and the deep models. That's very cool. You can also have all sorts of continuous values here, right? That just because I've been using dates, like don't think that they all have to be discrete. They can very much be continuous. So for things like, for instance, if we have a type called quantity with units, which generalizes extremely well. So you can use it for things like the wingspan of an airplane. You can use it for the melting temperature of a metal. You can use it for the height of a person. Now, it will be parameterized differently. Like, for instance, the prior over people heights will be different than the prior over airplane wingspans. But the rest of the operations will be reused across the board. And you can support a very large variety of properties with actually very few probabilistic property types. Right, okay. So now, how are we doing with time? We're okay. So now that we have the basis covered, let's look at the architecture. And this will be a partial architecture because, again, I can't fit it all on one slide. So starting with the various inputs, now we'll distinguish between three flavors of data that comes in. One of them is all of the unstructured sources alongside with their metadata. All of the structured knowledge that comes in as external KBs, and all of the user edits, right? Things like adding, removing, editing, and so on. Now, what we'll do is that we'll take them to a shared kind of, you can think of it as a canonical form. The unstructured sources will have to go through your favorite semantic parser. That is actually not it's not the focus of this talk, so I will not talk about how Alexandria does this, but there are many ways that you can do this. Then for the structured knowledge, you just have to map the schemas typically in order to map it to the schema of your knowledge base. And then what you have is these, what I call the strongly typed entity fragments, for the lack of a better name. So they are, at that point, they are entity fragments because they have the corresponding properties and property values. Okay, so we know at that point we constructed an entity, It is strongly typed because it has the corresponding types, but it's still potentially a fragment because we haven't put the pieces together. We just extracted them from somewhere, okay? So now what we have to do is to put them together in order to create the knowledge base. Now that putting together, I don't think we have a word for it. I call it linking and merging. You can think of it as distillation, condensation, I don't know, but it's not just conflation or just disambiguation, right? There is a part where things get merged into the knowledge base to construct the knowledge base. Right, so inside of this box, what happens is that we take these entity fragments, we convert them into probability distribution using the functions that I just showed, which I now call the probabilistic entity fragments, but these are really the ones that were converted into distributions. And now I can use the various operations of the distributions to deal with these. So for instance, I can compute the inner product in order to know how to link them. And I can now actually merge them via the element-wise product. And then I can put them in the knowledge base. And the thing is that I have to be able to do this continuously. Okay, so that data will keep on coming, and I will keep on adding it to the knowledge base. And again, the architecture is partial because in reality you have all sorts of user experiences built on top of the knowledge base that feed back into the human curation. So there is actually a loop here if you see the full architecture. Okay, now how do we do that linking? We do it through a generative model. And in this generative model, what we'll compare is these two scenarios. In the case where B is a new incoming fragment to the knowledge base, A is a fragment already existing in the knowledge base, and then we'll ask the perennial question, should B link to A? Okay. Now, in the first case, we assume, so A is always drawn from a latent entity E that we actually don't observe, and is given because we would go over the entities in the knowledge base, and then we'll do that comparison with the incoming entity B. In practice, you wouldn't actually go over all of the entities because the operation is actually massively sublinear because for many of those, you know that they're not going to link, but in theory, you have to do that. So in this case, in both of these cases, you can consider that A is given, right? And in the first case, both A and B would be drawn from the same latent entity. In the second case, they would be drawn from separate entities. Okay, so in the second case, they are independent. Now, what you want to do is to do model comparison of these two, see which one, you get some sort of a linking score and then threshold it, right? The way to compute this is that in the first case, if A is given, you actually have to go through E. So you go to the probability of E given A, then you go down to B, the probability of B given E, and you integrate E out, which gives you the probability of B given A. In the second case, because A and B are independent, the probability of B given A is the same as the probability of B. So that actually A does not participate in that computation, right? It doesn't matter what entity you selected if they were independent in this case. So all you have is just the prior over F, and then so you just have that right side component. You start from F, you take the prior of F, and then you go probability of B given F. Right, so then what happens is that we have to figure out now which one it is, so we have to compare them. This is done by taking the ratio, and this ratio decomposes very nicely into these two components. Now, the second one of these components is what would be, I guess, a parameter in the algorithm, but that's not a, it's an interpretable parameter, right? It's basically the number of entities that you have. I see Andreas trying to do the maths here. What you can do is that if you look at the joint distributions, might be easier on both sides, because then you would have P of A on both sides, and when you do the ratio, they'll cancel out. Yeah. Okay. Right. Okay. So the thing in orange is what would be a parameter, but you can approximate this parameter typically, roughly. It doesn't. You don't have to get it exactly right. And now the things in green we can actually compute from these operations that we previously defined in our probabilistic types. Now, how do we do that? We'll make an assumption that the entity is actually a joint, it's a factorized distribution over the properties. Now, that assumption might not be entirely right in all cases, but it's often okay. So what this means is that the properties have to be independent, right? So you assume that your name doesn't depend on your date of birth, for instance. Sometimes it might. Maybe people called January are more likely to be born in January, but in practice, no. So if it happens in practice, what you can do is that you can actually build a correlation model on top of that. You don't have to assume that factorized distribution, right? But if you do, then you just directly send the responsibility to the probabilistic types, and they just do the work for you, right? And that is really cool. I think that is super cool, because assuming that factorized model, the heavy lifting is done by the entity types, the probabilistic property types. And I think it's amazing. Now, I haven't discovered it, so the credit should really go mostly to John Wynn. So I can praise it. The reason why I love it, there's probably at least maybe 3 reasons. So first of all, it's very composable, right? So you can keep on adding new property types, and you can build the models for those probabilistic property types independently. And you can build them up, which is very, very nice that it's modular and composable. Secondly, it really allows for things like, as I gave the example with embeddings, to be incorporated in this framework, right? So you truly have probabilistic modeling and deep learning working together, which I think is the direction that we have to take very seriously. Now, finally, what is, I guess, the point of this deck is that it supports all of the requirements that I talked about, okay? It supports human curations, because they get converted again into the entity fragments. It supports incremental learning, because data, even in this example, comes in and you know how to incorporate it in the knowledge base, and so on. So, very, very cool. Okay, how am I doing with time? I have 10 minutes. Okay, cool. All right. I'll go to the future of the project then. All right. So so in order to go to the future, I firstly have to start from the past, right? In 2019, we presented the first version of Alexandria here, actually at AKBC. And the way it was used in an application, it was actually discovering data from the internet, and it was powering some search-based experiences. Okay. Now what we have is what we call Enterprise Alexandria, and this is the version that does a little bit more than search. Now it still does search, it still supports the search in the knowledge base, but also now starts surfacing these entities a little bit more proactively in various experiences and in people's workflows, right? It allows you to do a hashtag now, it would automatically highlight an entity while you work. So it's a little bit more proactive, right? So if I look at that timeline, I would say that on the left, the knowledge system was kind of sitting there passively. It was waiting for requests. Now it's becoming a little bit more proactive. So what you would want to see over time, and what we're thinking about the next version, is something that can actually truly guide your workflows. So the dream is to have this AI-guided knowledge work, okay? And for this, the knowledge base has to be very rich, it has to be very reliable, and so on. I'll give a quick example of what I mean by this passive and active knowledge, because this is really where we see knowledge systems having potentially a lot of impact. If you take a passive example where a person would ask, does anyone in our group have machine learning experience, right? Now, maybe they ask this because they actually need colleagues who can help them with the task that they're doing right now. So if we had all of this context, if we had modeled their workflows, and if we have in our knowledge base all of that information, then we can surface it to people proactively, right? Another example, when is feature X expected to ship? What the person is probably thinking, wow, what are all of the remaining activities that I need to do before feature X ships? And this is another thing that the system can proactively surface. And there is a lot of interest for this, and if we go there, we really need to develop a very rich and reliable system. And maybe what I'll talk about the next time is a foundation model of knowledge that we'll have to build for this, but not today. Right, thank you.
Okay. Any questions from the room at all? There's one. I'll come to you first.
Thank you for the talk. It might be a bit out of scope, but do you have any plans to support languages that are not English?
Yes, we already do. Yes. So I, again, because I had to select some of the requirements and focus on those, I didn't talk about multilingual, but that is something that we already support. So we already support almost all what we define as tier 1 languages, and then we'll be expanding to 200 more.
And does everything you talked about today translate seamlessly to other languages? Because it sounds to me that you're missing a lot of component.
Good question. So a lot of this actually does. A few things don't quite do. The framework does, but when you actually start implementing them, in order to implement them efficiently, you actually have to do potentially things differently. For instance, the tokenization in Japanese might be different, and because of that, you might need to further optimize it. But the framework that I presented actually very much does translate across languages, yeah.
Thanks.
Great, thanks for the very interesting talk. So that you mentioned schema mapping and semantic parsing as two different approaches for ingesting these knowledge.
Yes.
And I was wondering how this would deal with something like spreadsheets, which seems kind of in the middle, semi-structured, but not quite.
Yes, it's a very good question. And that's something that I really did not tackle in this talk because I focused on that upper part of the diagram. We do have our very, very first example of Alexandria was one that actually works in Excel. We had it a very long time ago, and it is a separate problem to solve. I think that the schema mapping is a separate problem to solve, and not one that I actually have incorporated in this framework.
Right, thanks.
Right, thank you. I've got a question from online from Mike. How do you handle inconsistencies, and can Alexandria flag these automatically?
Yes, we do. Another thing that I didn't talk about, but we support. Actually, I think in the 2019 paper we published that, and we explained how it works. So what happens is that when you do the merging, you can actually support alternate values. So you can decide that, hey, look, these two entities are referring to the same thing, but to the same entity, but their corresponding properties had different values. Choose to actually maintain both values and acknowledge that they are alternate values, right? In some cases, you wouldn't do that. For instance, you can choose to, in the case of topic pages, if you have one topic that comes with a certain set of people and another topic that comes with a certain set of people, and you realize, oh, these are the same topic, then the collection, you can choose to merge the collections. But if you look at the various thresholds there, you can actually decide that they're different enough that you keep them as alternate values. So yeah, it is in the framework.
Okay.
I think there's...
You have a question?
Yep. Thanks.
Sure.
So I think you mentioned this in passing. So about maintaining kind of the relationship with the user and making sure their views of the data is not changing too much.
Yeah.
So if you have some errors that you have done in the past and that you are very sure right now needs to be fixed, so how do you kind of inform users just to make sure that the users are also on the same page?
Yeah, very good question. So so actually the whole user in the loop, I think, is another paper or a book. What you would do is that you would, so first of all, the user curations, but we call them curations like user edits, they would be stored separately. So if the user has done something, we actually assume it's the ground truth. We assume that the human curation to a topic is correct. Okay, so this is one way of handling, I guess, inconsistencies. Maybe I should have mentioned that. But over time, if there are errors, if the if we detect errors against the human curation, we'll preserve the human curation. If we correct for our errors, we would actually change them directly. I don't know if we have an experience that explicitly raises a flag for that, but given how often values change, I think it will probably be overwhelming to raise alarms for that. So it is preserved in the knowledge base. You can go and see the changed value, but I don't think we will alert the user for the change. Do you think we should? I don't know. Probably depends on how they use that topic, right?
Yeah,
it depends on the experience.
Importance of that change also.
Yeah, exactly. Yeah, exactly. So in the current experiences, I'm not sure, but in the future, definitely. Yeah.
Okay, there's another question online. Is there any more questions in the room? Or? So there's a question about the privacy requirement and eyes off. So how can you validate that the model works well on customer data without being able to see their data?
Tough, very tough. Okay, so it's difficult. So the way the evaluation works is in very many stages. Firstly, you would have unit tests, I guess, and then you'd have some sort of experimentation setup on some data that is visible to the people in the team, right? Then what you can do is that you can have an evaluation on a bigger set of data that different people might not have a consistent view over. And this is because some of them might not have permissions to some of the items in this data. So I guess just by virtue of being employee in the corresponding company, you have access to certain documents, and a lot of what we extract is from documents. So you can actually run the algorithm on this and see what you can see. Right. So for instance, if there is some tented project, I will not have access to these documents, and I will not be able to see them. So I will not be able to debug properly these errors. So that's one step of the evaluation process. Then what we'll do is that when we productize these things, they'll go through various rings. So they'll firstly go to Dogfood, then they'll just go to various rings, Microsoft, and they'll go only then to some tenants and then to all tenants. So in each one of these steps, you can actually get feedback. And in some cases, people can choose to share something with you, right? They can say, oh, that's actually okay to share here, right? And they can give you data, and they create these, what we call dissats or dissatisfactions. And they would give this to you so you can actually debug the problem. When we go to external users, they actually also sometimes choose to do that, which is very nice. In other cases, we also can talk to what we call here the knowledge managers, because the various organizations have their knowledge managers who have access over the management portal of the topics. And with some of these, we maintain a closer relationship, and actually we speak to them and they give us feedback on the various problems.
Okay, let's thank our speaker one more time.
Thank you.